So good afternoon, everyone. So we are meeting after 2 weeks. Hope you had a good and relaxed time. So now you need to really kind of to be on kind of study mood. So let's start. So now the plan for today is to kind of start the second chapter or second topic in the second section. But before that, let me go through the sections or the topics that we have covered before the holidays. And I think I have one topic left. We have one topic left to discuss. So I will discuss that one as well. So now, as you know, so we have one more week in April where we are going to meet online. We don't know what's the plan for May. So let's see whether we are going to again meet online or you are going to come to the university. But anyway, next week also we are going to meet online. So therefore, please ask questions if you have. I hope you studied a bit during your holidays. So please ask if you need any clarification, if you have any question. Yes, I forgot to upload the CA, the continuous assessment, third continuous assessment. I will do that. I will do that by today. Okay, I also forgot that one. Okay, yeah, so let me go to the first topic that we have discussed. Now, before that, so please go through these pop quizzes and this practice worksheet. I saw a couple of you have already kind of tried these quizzes. So please go through this one. This is kind of a practice questions for you. We are not going to discuss these ones in the class, but these are for you to kind of practice the materials that we have discussed. Okay, and there are a couple of quizzes, practice worksheets on the topic that we are going to discuss today as well. Okay, so before that, let me go to the topic that we have covered during last few weeks, the sampling and the sampling distribution. I'm not going to kind of discuss the materials again and again, but I will try my best to kind of give you a overall idea what we have discussed there. Okay, so these are the topics that we are going to kind of discuss during, in the second section. So today we are going to discuss this confidence interval estimation, and I will kind of first we'll go through the sampling and the sampling distribution. There's one thing that we need to discuss, the sampling distribution of the proportion. We have already discussed sampling distribution of the mean, but we haven't covered the sampling distribution of the proportion. We'll discuss that one as well. So now, so in this topic, the sampling methods and the sampling distribution, we have discussed a couple of sampling methods. I hope you understand that part. Let me directly jump into the sampling distribution. Okay. So now sampling distribution, it's a distribution of a let me go through from here. Now, distribution is a kind of a distribution of, let's say, distribution of a variable. It's a kind of a distribution of the variable. Means now variable can take different values. So once we kind of, let's say, once we plot those the values on a diagram, then we can have some kind of a shape. So that shape, we call that one as the distribution of that particular variable. So basically, we can have distribution for a population, so distribution for a whatever statistics. Okay, so the population distribution or a distribution for a population means It's a distribution of a particular variable among all individuals, because we know a population contains the whole kind of the all individuals or all units in a kind of a target population. So if we know the values of values for all the individuals, let's say if we take our probability, our stat class, let's take that's our population, and if you know if you let's say we know the weight of all of the students in our class, then it gives actually kind of a distribution of the weights. Okay, distribution of the weights. Sorry, one moment. Let me. Yeah. So distribution of the weights of all the students in our stat class. So it's a kind of a, I mean, you can find some kind of a shape of those values of the kind of the weights. So yeah, so for example, the population distribution of heights in a country, like, or population distribution of the weights in our stat class, like. Then I mean, when we have a population, we know I mean, with the population data, we consider the parameter because the parameters are the kind of the numbers or the values that describe some characteristic of a population. So we give a specific name for that number as a parameter. So parameters, so we can have a population mean, population standard deviation, population proportion. So with the population value, so the I mean, with the population data, we use this Greek letters to kind of denote those values. Population mean for mu, population standard deviation, we use sigma. Then the population proportion, we use capital P. Usually, the parameter values, population parameter is an unknown value where we try to find, or we try to, I mean, better word is try to estimate that parameter using a given sample, or using a sample that we take, that we get using different sampling methods. So that's where we discuss those types of sampling methods. So based on the sampling method that we use, we take a kind of a representative sample to calculate or to estimate the value of the parameter. So simply we can find the population mean using, or we can estimate the population mean using the sample mean. Similarly, we can estimate the population standard deviation based on the sample standard deviation. And also we can estimate the population proportion based on the sample proportion likewise. Then the statistic, same as the parameter, statistic is a kind of a number that we used with the sample. So the statistic, statistic is a known value because we know, I mean, we can get a sample out of the population, and then we can calculate whatever the relevant value, let's say sample mean or sample standard deviation or sample proportion, we can calculate those values. So the statistics is a known value, whereas the parameter is an unknown value. But we can use the statistic, to estimate the parameters. Simply, I mean, you can think we simply use the statistic as an estimate for the parameter. So yeah, statistics are estimated from the sample data, and we use those to estimate the value of the respective unknown population parameter. Now let's see what's the sampling distribution of a statistic. Now you know, I mean, when we take a sample out of the population, we can take different samples. Okay, so we can take different samples, different sample out of the populations. Okay, take now, let's say, so this is our population. Okay, so this is our population. So we can take one sample, let's say S1, sample 1, and we can take another sample, S2, then sample 3. Okay, so likewise, we can take infinitely many samples. Let's take this one as 1,000 samples. Likewise, we can take different samples, and let's say we calculate for the first sample, we calculate the sample mean. Okay, you know how to calculate the sample mean. Simply, we take, let's say, we are the variable that we are interested is. Let's say we are the variable that we are interested is weight. Okay, weight. Then we can calculate. Now in the sample, we know we have a couple of individuals. So we can calculate the sample or the mean, the mean weight. Okay, mean weight. How do we calculate? We take the sum of all the weights, all the weights of all of these individuals in this sample, and then divided by the number of individuals in this sample. Okay, so likewise we can calculate the sample mean for the sample 2, then sample 3, and here also we can calculate the sample mean for this 1,000 sample. Okay, now you see we have 1,000 means, 1,000 sample means. Okay, 1,000 sample means. 1,000 sample means. Okay, and now let's assume here we have the same sample size. Like so, let's say we take a sample. We take this sample with sample size n. Here also we have the sample size n, sample size n, sample size n. Okay, so let's assume that we take a sample of the same size. Okay, so given size. Okay, let's say n. Okay. Now you see, so now we have 1,000 sample means. What we can do actually, we can kind of, now we have 1,000 sample means. Okay. So now we can kind of plot these 1,000 sample means on a diagram. Okay. So let's say we have here let's say sample number. Okay, sample number. And here we denote the sample mean value. So then the first sample we have, let's say sample mean here. Then the second sample, let's say sample mean here. Third here, and then 1,000 somewhere here. Likewise. Okay, now you see. Let's say, so this is kind of the shape that we have. Okay, now you see, so with this 1,000 sample means, we can have again a kind of a distribution. So we call this distribution as the sampling distribution of, we call this one as the sampling distribution of sample means. Because now we are using sample means here. Okay, so we call this one as a sampling distribution of sample mean. So sampling distribution, so similarly we can have sampling distribution of sample standard deviation, sampling distribution of sample proportion, depending on whatever the statistic that we consider, that we use, we can have a sampling distribution. Because now you see here, instead of calculating mean, we can calculate sample standard deviation. Okay, S1. Now here S1 is the standard deviation. Let me write here instead of S, let me write here standard deviation. Okay, so we can calculate standard deviation for sample 1. And here, instead of the sample mean, we can calculate standard deviation for sample 2. Likewise for sample 3, and here we can calculate the standard deviation for 1,000 samples. So now if we consider the sample standard deviation, we can again find another distribution. So we can call that distribution as sampling distribution of sample standard deviation. Now our statistic is the standard deviation. So depending on the statistic, depending on whatever the statistic that we can use, we can define a sampling distribution. Now here we especially use only two, in this class, we use sampling distribution of sample mean and sample proportion. Sample proportion is the one that we are going to discuss today. We already discussed this part. So we simply discuss sampling distribution of a sample mean and sampling distribution of sample proportion. So now, if we take now single value of a statistic that obtained in practice, it's just now, if we consider just one value here, so let's say we consider this value. So this is just a one single value of a statistic that we can take or that we can take out of this sampling distribution. So this is a kind of a one value. So we call this one as the point estimate. This is a point estimate. Point estimate is just a one value of this whole sampling distribution. So just a one value. Now today actually we are going to consider this confidence interval estimate. Now here point estimate is just a single value. Just a single value. Confidence interval estimate means now instead of considering just a one value, we are going to give a kind of an interval here. We are going to give an interval. Kind of, let's say this sample means is in between, let's say 50 to 100. So here we can take whatever the values in between 50 to 100 as the sample mean. Okay, so this is what we are going to discuss today, how to find a confidence interval for a given mean, for a given sample mean. The confidence interval for a mean and confidence interval for a proportion. Okay, so that's what we are going to discuss today. Anyway, so before coming to that, let me kind of give you the idea about, again, the sample mean and the sample proportion. I hope this is clear to you. Okay, so yeah, so the point and the confidence interval, again, point is just a single value of a statistic. This is the kind of the point estimate. Okay, confidence interval is kind of we are giving a kind of a range of the values that we can take as the population or as the mean or as the proportion. So now, so now let's see. Now we discussed this one using R. We discussed this question. Oh, this we discussed this activity using R. Now, why do we consider sampling distribution of a statistic? Because we should understand why we consider sampling distribution instead of just a one value, because a single sample statistic, or for example, like the sample mean, we should understand it's just a one value, one single value, or one realization from many possible samples that we could have drawn from the population. Now, if you consider the previous picture, now here we see we can take different samples. So we can draw different samples out of this or from this population. Now, sample statistic, single sample statistic or sample mean, one sample mean is just one realization from many possible samples that we can draw from this population. So we see if we take different samples, we will get different values, right? So therefore, that's why instead of considering just a one sample and a one sample mean here, we prefer to consider a sampling distribution of that sample mean or whatever the statistic that we use. So simply the sampling distribution describe all possible values the statistic could take. And actually, the sampling distribution shows that statistics or that the values that we take for the given statistic or here the sample mean vary from sample to sample. Okay, so that lets us understand. I mean, using this sampling distribution, we can understand, actually, we can see whether the given statistic is a kind of unbiased or whether it's a biased value. And we can see the variability of these sampling means. And we can simply, or we can see the shape of this sampling means. So there are a lot of kind of the advantages of using this sampling distribution of a given statistic compared to consider only the point estimate. So now, the second question, why is it not enough to look at a sample statistic? Because, I mean, if we consider just a one sample statistic, it doesn't tell us anything about the uncertainty. But if we only consider just a one sample statistic, we don't know how close it is to the true population parameters. Now, we know we use this sample and we use this sample statistic to say something about the population or to say something about the population parameter. But if we consider only just a one sample, we don't know that the sample mean or whatever the statistic that we calculate using that sample, we don't know how close that sample statistic or the sample mean is, how close that sample mean is to the true population parameter. And we don't know actually how much it would change if we resample. We don't know whether that calculated sample mean change if we resample. Of course, if we take another sample, we will have a different sample mean. And we can't, also we can't judge whether that sample mean or whether the value that we get for the statistic is kind of a reliable, or whether it's due to the random change or random chance. So therefore, instead of considering just a one sample and a one sample statistic, so that's why we prefer to consider sampling distribution, because the sampling distribution gives us, if we use the sampling distribution, then we can we can find kind of a more reliable or more kind of accurate value as an estimate for the true population parameter. Also, we can use the whole sampling distribution as I explained here. We can consider the sampling distribution to calculate even or to build confidence interval. That means a range of plausible values that we take for the population parameter. And also we use this sampling distribution in hypothesis testing. That is the last topic that we are going to discuss under the second chapter. So you can think, so very simple example. We can let's say we can take, let's say can think a sample statistic as just a one snapshot. Let's take a movie. So the sample statistic, we can consider the sample statistic is just a one snapshot. Then the sampling distribution will be the full movie of what could happen. Okay? So we know without the full story or without the full movie, we can't tell whether our snapshot is kind of typical or the unusual. So by looking at just that snapshot, we can't tell the whole story. So we need to kind of look at the whole movie to get an idea about the story. Yeah, so that's why, I mean, that's just a kind of the example. So similar to that one, to get the full understanding or full picture about our population, so we prefer to use a sampling distribution of sample mean or whatever the statistic that we use instead of just a one single value. Okay, so that's why we use this sampling distribution. That's why we are discussing this whole sampling distribution concept. Okay, I hope it's clear to you now. Okay, so then, yeah, we discussed this example and we saw the result. What happened when we increase the number of samples that we take. We saw, okay, when we increase the number of samples, we see the sample mean, the distribution of the sample mean is a kind of a very, we had a kind of a very symmetric distribution there. Okay, maybe let me, yeah, let me quickly go through that one as well again. Okay, one moment. So yeah, if someone missed the last class, let me open that activity and quickly let's go through that one as well. Yeah. Okay. So here now this is the activity that we discussed last time. So let me quickly go through this one again. Now, first, I try to kind of generate a population. Okay, so this is the population we have. So this is the population data. So we have actually 100 individuals here. I'm considering, let's say I'm considering height. Okay, height in inches. No, height in feet. Okay, so let's say, so here we considering the height of 100 people. Let's say in the population, we are having simply 100 people. Okay. So now let's calculate the population, the mean of, so these are the heights. So I'm going to calculate the mean of this population data. So we have the mean as 5.1. Okay, let's say 5.1. And we can calculate the standard deviation as well. So the standard deviation is, let's say, 0.89. Okay, then I'm going to kind of take different samples out of these population. So I'm going to take a sample 1. Okay, and let's see what are the values that we have here. So these are the sample size is 20. Now we have, so these values are, I mean, we draw these values from this population or the whole population data. Okay, now we have 20 values here. Okay, 20 values. And let's calculate, we can calculate the mean of these values as well. That is the mean of the first sample. It's, we see, okay, it's 4.9. It's around 5. Let's say it's around 5. And the standard deviation is around 0.87. Okay, likewise, we can take another sample. Now I'm going to take the sample 2. Let's say, let's see the values here. These are the values. Now you see we are having in the first sample, we are having different values. Okay, now this is the sample the values in the first sample, and these are the values in the first sample, and these are the values in the second sample. Now you see the values are different, okay, because we are kind of randomly drawing values from the population. So this is our population. Population contains 100 values. Each of these sample contains 20 values. Okay, so likewise, so similar to the first sample, we can calculate the sample mean. It's again around 4.9, and the standard deviation. Now standard deviation is 1.0 something. Before, the standard deviation is 0.87. Okay, the mean is 4.99. Now, for the second sample, mean is 4.98. Now you see, based on the sample that we are drawing from the population, we have different means and the different standard deviation. Okay? Similarly, we can take a sample, third sample. Okay, so let's look at the values here. Okay, likewise, we can calculate the mean. Now it's again 4.94. Standard deviation now, if you look at the standard deviation, our standard deviation is 0.59. Okay, now you see, based on the sample data, we have different means, different standard deviation. Okay, now I'm going to kind of, let me take fourth sample, fifth sample, 6, 7, 8, 9, and 10. And let me calculate the mean of all the samples. Okay, so these are the, now if you look at these values here, these are the sample means of those 10 samples. So we see in the first sample, we have 4.99, second sample 4.98, then the third sample 4.94. Likewise, then this is, yeah, this is I think this is the eighth sample. Eighth sample 5.41. The fifth sample 5.02. Likewise, so we have different. I mean, these are not the same values. We have different mean. Okay. Now what we can do, I'm going to take the mean of these mean values. Mean of these means. Okay. So the mean of those means will be 5.03. So 5.034. 5.034. So this is, now we call this one as the mean of the sampling distribution of the sample. So these are the 10 means. What I did, I calculate the mean of all these 10 values. So then the value will be 5.03. So we see, so we call this value as the mean of the sampling distribution of the sample mean, because we are taking the mean of the 10 sample mean. And we see this is actually a bit closer to the population mean. Now, population mean is actually 5.10, and the mean of the sampling distribution of the sample mean is 5.03. This is bit close to the, or bit closer to the population mean. Similarly, we can calculate the standard deviation of all of these sample means. Let me calculate that one as well. Then we call this one as the standard deviation of the sampling distribution of the sample mean. Okay. And what I'm going to do, I'm going to kind of, so I'm going to, so this is the value. Yeah, I will skip this one for a bit. And now what I'm going to do, I'm going to kind of draw a histogram using those 10 samples. I'm going to kind of plot histogram of the sample mean. Now you see here, if you look at this one, now you see here we consider 10 samples, and you see the distribution is right skewed, because we are using 10 sample of size 20. Okay, of size 20. Now this is a kind of a skewed one. Now, instead of considering 10 samples, I'm going to consider 10,000 samples. Okay, so this is where we kind of use a for loop to kind of generate 10,000 sample with the sample size 20. Sample size is 20, but we are considering instead of 10 samples, I'm going to consider 10,000 samples. Okay, and let's see the histogram of that sample mean. Okay, now what happened? Now here we are having a skewed one because we only consider 10 samples. Now here we consider 10,000 samples of sample size 20. Sample size is 20, but the number of samples now we increase. Now what we can see? Now we see, okay, now the sampling distribution of the sample mean is a very symmetric kind of a shape. Actually, this is a kind of a norm. I mean, we can say now the sampling distribution of the sample mean is normal. Now we are having a symmetric bell-shaped distribution. Okay, so you see, when the number of samples increases, we can have a very kind of a symmetric one. In the previous one, here we have 10 samples. That's why we are having a skewed one. But when we increase the number of samples, for example, the 10,000 samples of the same size, now we are having a symmetric one. Okay. Now, if we calculate the sample mean of these sample means, or I mean, the sample mean, the sample mean of this distribution, or the mean of this distribution, it will be actually 5.11. This is almost equal to the population mean. Now, the population mean is 1.1. And if we calculate the mean of these 10,000 samples, the mean of the sample mean, then we are having 5.11. So this is almost equal to the population mean. Okay. Now, let me close this one a bit. Now, let me skip this one. Here, this part. Now you see the sampling distribution, this part, sampling distribution of the sample mean, actually, it's very close to the population mean. This is the population mean. And the sampling distribution of the sample mean, the standard deviation of the sampling distribution of the sample mean will be sigma over square root 10. This is the part that I skipped from the R activity. Let me go to that one again. So you should understand this. The standard deviation of the sampling distribution of the sample mean will be sigma over square root 10. Okay, let's go back to the R activity. Now here, this part, this line. So here I'm trying to calculate the standard deviation of the 10 samples, standard deviation of the now here. So this is the So this is the mean, the sample mean of the 10 samples. Okay, so I'm going to calculate the standard deviation of these 10 values. Okay, so it will be simply 0.15. Okay, now I'm going to calculate that sigma over square root n, that is the standard deviation of the population divided by the square root n. Here, now you see these two values are, bit different. Now, the standard deviation of the sampling mean, it's 0.15. Then the sigma over square root 10, this part is sigma over square root 10, it's 0.2. We can say a bit close, but here we are having 0.1, here we are having 0.2. Okay, now let's see what happened when we increase the number of sample, let's say 10,000. Okay, so I'm going to now calculate or now consider the 10,000 samples. Now this is the, now you see here. So this is the standard deviation of the mean, standard deviation of the mean of the 10,000 samples. Now it's 0.18. So here the sigma over square root n is actually 0.02. Okay, let me copy this value here. Okay, so this is the value that we have here. Okay, now you see, if you look at this line, now you see, so the standard deviation of the mean is 0.18. This is very close to actually the sigma over square root n. It's 0.2. This is very similar. I mean, this is very close to the 0.2. But what happened when we consider only 10 samples? 10 samples, we understand here 0.15, but this is not that much close to 0.2. But if we increase the number of samples, then we can have a standard deviation of the sample mean, which is very close to the sigma over square root n. So you understand. So I hope you understand the whole concept that we are trying to kind of study here. So from the whole kind of the activity, we should understand, okay, now the mean is actually very close to the, now this is the mean of the 10,000 samples. This mean is actually almost equal to the, so this is the mean of the 10,000 samples. I mean, mean of the sample means of the 10,000 samples. This is almost equal to the population mean. Okay. Here we have 5.108994. Population mean is 5.108887. So these are almost equal. And the standard deviation is also very close to the sigma over, now here sigma over square root n. This is close to the 0.2. Now instead of 10,000, if we increase, let's say 100,000, instead of 10,000, I'm going to generate 100,000, and let's see what happened then. 100,000, it will take time. Okay, still R is running here. That's why we are having this red kind of the what do you call it? Small notation here. Okay, red kind of the notation. So still R is running because now instead of 10,000, I'm trying to kind of consider 100,000. Okay, so here I increase the samples, number of samples. Okay, yeah, it will take time. Okay. Let's wait maybe 1 more minute. Okay. Otherwise, I will stop. Let's see. Let me interrupt. And instead of 10,000, here, let me introduce 15,000. Okay, now, in the previous example, we considered 10,000. Now I'm going to consider 15,000. Okay, 100,000 is bit, it takes time. Okay. Let's see. Because now R is calculating, I mean, generating 50,000, yeah, 50,000 samples, and calculating, yeah, 50,000 samples. So it takes, I mean, it producing or resampling 50,000, so it takes some time. Yeah, while it's running here, let me go to the note. Now, yeah, so now now we understand, okay, so the sampling distribution here, sampling distribution of the sample mean is the distribution of all possible sample means. If we collect or if we select all possible samples, here we consider simple random samples. I mean, we are using the simple random sampling method to get the samples. So the sampling distribution of the sample mean means, so the sampling distribution of the sample mean, X bar means the sampling distribution of all possible sample mean. Okay. Then from theory or from, from calculations, we can show then the sampling distribution of the sample mean has the mean. So the sampling distribution of X bar actually has the mean mu, this is the population mean, has the standard deviation sigma over square root n. So this is the population standard deviation divided by the sample size. So we call this part actually the standard deviation sigma over square root n. We give a kind of a special name. We call this one as the standard error of the mean. Standard error of the mean. Okay. So this value, so this is the value of the standard deviation of all possible sample mean. Okay. Now you should understand this is the standard deviation of the all possible sample means, and it expresses how the sample means vary from sample to sample. And we understand when the sample size n increases, the standard deviation or standard error of the mean decreases. Okay. When sample size increases, this whole value decreases because we are dividing this sigma by a large value, then this whole value will be smaller. Okay, so when the sample size n increases, the standard error decreases. Okay, so let's go back to R. Okay, it's still running. Okay, it takes time as well. Okay, now it's done. Now here 50,000. Now I'm going to calculate the means of those 50,000 samples. Now, if you want to look at the values here, now you see here, so this is the kind of the sample means of all those 50,000 samples. Okay, so you see here we are having 50,000 values. Okay, 50,000 values. Now what I'm going to do, I'm going to kind of draw a histogram. Now you see again we are having very symmetric, or we can say bell-shaped, or kind of now the sample means are kind of distributed as normal. Okay. Now I'm going to calculate the mean of these 50,000 means. Now we see, okay, this is the value here. This is the value now. So we see, now you see, now compare the values here. So now the mean is actually almost equal to the population mean. So this is the actually the mean of the 50,000 sample means. So it's 5.108, and this is the population mean mu. This is 5.10. Okay, now if we calculate the standard deviation of that 50,000 means, now we see, now we are having actually 0.178. Okay, we can say, okay, this is kind of close to the sigma over square root n. Sigma over square root n is 0.2, and here we are having 0.17. Yeah, the standard deviation is not kind of the almost equal, but we can say, okay, approximately equal to the sigma over square root n. Okay, so you see, so from this R activity, what we can see here, we can see the sampling distribution of the mean has mu, that is the population mean, and the standard deviation will be sigma, population standard deviation divided by the sample size. Okay, so that's what we try to see from that activity. Okay. Yeah, then, before coming to this one, we discussed two kind of the laws. First one is the sample mean X bar approaches to the population mean. Okay, so that means X bar approaches, if we use notation, X bar approaches to the population mean. So this is sample mean. Okay, sample mean, this is population mean. Okay, now X bar approaches to sample mean when as n increases. That means n goes to infinity. And when n is, let's say, n goes from, let's say, n increases to 10,000, we can say, okay, sample mean approaches to the population mean. So that's what actually we saw from our R activity. So here you see sample mean. So here we are considering 50,000. So sample mean now almost equal to the population mean. Okay, almost equal to the population mean. Let me erase this drawing. So sample mean almost equal to the population mean when n increases. N increases. Okay. Here actually the n is actually the sample size here, not the number of samples. Sample size increases. I mean, we can we can see the same when the sample size increases also. We can see the sample mean actually approaches to the sample population mean. Okay, but in the R activity, we saw when the sample, number of samples increases, we see the sampling, the mean of the sample mean actually approaches to the population mean. It's the same. I mean, we can show this one as well when the sample mean approaches to the population mean as the sample size increases. We can show this one also through the R activity. Okay, you can see this one when you are doing your continuous this third continuous assessment. Okay, I will give you a question to show sample mean X bar approaches to the population mean when the sample size increases. Okay. Okay, then that is the first law, and then the central limit theorem. This is a kind of a very, very important theorem in statistics. This means when n is large, when the sample size, now here the sample size again, when n is large, we can say the sampling distribution of X bar is approximately normal. So from the R activity also, we see when the number of samples, now here the number of samples, but we can prove this one as well. When the sample size is large, we can say the sampling distribution of X bar is approximately normal. We can show this one as well. Okay, that part is for you to do in your continuous assessment. So here we see what happened when now if you look at the diagrams here. So here we use 10 samples. Then here we use the 10,000 samples, and here we use the 50,000 samples. Okay, now what happened compared to this one? Here we are having very symmetric or normal curves or bell-shaped curves. So here, when the number of sample is large, or when n is increases, we see the sampling distribution. X bar sampling distribution of sample mean is approximately normal. Okay, normal. So here n is not Here n is the number of observation in each sample. We can prove this one as well using that kind of R activity. That part is again for you to check or you to do when you are trying, when you are doing your continuous assessment. Okay, the third one. Okay, now let's look at these three observations again. The first statement explains here. Now, if each individual observation is taken from a population having a normal distribution, that means here what we do, let's say we have a population and all the population now, population data, here the X bar, X, these observations. Now the population is actually, the population now normally distributed. Okay, so the population or this observation now have observations now have normal distribution, or we can say, okay, all the observation now normally distributed. Okay, then what happened? Now, then the X bar means, now we can take, I mean, from this population, we can take sample 1, sample 2, likewise, let's say 1,000 samples. And then we calculate X bar for each of these samples. Then what happened? Now the population is already normal. Therefore, we can say, now we know we are having 10,000 sample means, sorry, 1,000 sample means. Then if we draw this one on a, let's say on a diagram, we see, okay, now the sampling distribution, the shape will also be normal. So that's what the first statement explains. Okay, so if each individual observation is taken from a population having a normal distribution, then X bar, this is the sampling distribution of X bar. Okay, this is the X bar means here sampling distribution of X bar here. Okay, sampling distribution of X bar also follows a normal distribution because the population is already normal. Population is already normal now. Sampling distribution of X bar is also now normal. Okay, that is the first state. Then the second statement says, population doesn't follow the normal distribution. Now we don't know the distribution of the population. This part we don't know. And we take again, let's say 1,000 samples where n is now large. Now here, let's say sample size of each of these samples here, this should be greater than or equal 30. And if n is large, this is the kind of a rule of thumb. Usually 30 or more is, I mean, in statistics, 30 or more, we consider 30 or more is a kind of a large sample. Let's say instead of, let's say here, let me take 50. Now, here, we take sample of size 50. Each of the sample size is 50. Now, in the previous case, in the first, under the first statement, we don't need to have this 50 or we don't have this condition when n is large here. Under the first statement, we don't need this condition when n is large. Here we can have simply n equal 10, even, I mean, n equal 20, whatever the n value, we can consider under the first statement, because here the population is already normal. But in the second statement, we don't know the shape of the population. We don't know whether the population is now normally distributed. But still, if we take the samples of size, let's say 50, or samples of size greater than or equal 30, then we can again say, now here we consider 1,000 samples of sample size 50, and we calculate the sample mean, and we draw the distribution. Again, as we are considering this large sample sizes, we can again say, okay, now the sampling distribution or the shape of the sampling distribution is again normal, though the population doesn't follow a normal distribution. That is comes under the second state. In the first statement, we have normally distributed population, and therefore the sampling distribution X bar is normal. But in second statement, we don't need to have the population follows the normal distribution. But if we take sample size, large sample size, then we can again say, okay, sampling distribution is now normally distributed. Then the third condition, third statement says, if the population distribution is not normal and the sample size now is small. Now here population is, we don't know the shape of the population, and now here we have small sample size. Can N50 again away. For example, let's say N10. N10. So we are now, now we are taking sample size. We are considering 10 sample size is 10. Now, now what happened? Population is not normal and we are considering sample size, small sample size. Then we cannot say the sampling distribution of X bar is normal. We can't say this one. This doesn't hold. Okay? That's why if the population distribution is not normal and the sample size N is small, the sampling distribution of X bar can take any shape. We can't specify the distribution of X bar. We can't say, okay, now the distribution of X bar is normal. We can't say that. Now the distribution of X bar can take any shape. Okay, that comes under the third statement. Okay, I hope now it's clear. Now it's clear to you the shape of the distribution of X bar, whether it's normal or not normal, depending on the distribution of the population and the sample size. Okay, is it clear to you guys? If so, please just use the chat and say it's clear to you, at least one or two. If it's clear to you, just let me know whether it's clear to you guys. Yes or no? Yes, okay, yes. Okay, good. Thank you, guys. Thank you. Okay, very good. Okay, now, okay, then, so those are the two laws comes under the sampling distribution, law of large numbers and the central limit theorem. Okay, this part, I will give you a question in the third continuous assessment. You can use R to kind of show this or demonstrate this, or clarify this statement as well. Okay, now then the standardized Z values for the sampling distribution. This part is very similar to the part that we discussed before under the continuous distribution. So now for the sampling distribution X bar, we are now going to use the normal distribution. To do that, we need to convert, or we need to use this transformation. Simply, we are using this transformation. In the previous, under the continuous distribution, we use Z as X minus mu over sigma. Over sigma. This part comes under the continuous distribution. Continuous distribution. That is the topic that we sorry. Okay, continuous distribution. This part comes under the continuous distribution, this transformation. Then we can find x as simply mu plus z sigma. Okay, similar to this one. Now here we are using z instead of x. Now we have x bar, and we know the mean of the x bar is actually mu. That this is comes under the law of large number, and instead of sigma we use here sigma over square root a. Okay, this part comes again from the sampling distribution of sample mean. Then here, similar to this one, we can find x bar. X bar now will be mu plus z sigma over square root a. Okay, so we can use this transformation back and forth. Actually, both sides are correct. So we can use this transformation. If you use this transformation, we can use the table to find the probability. We can use the z table. Okay. Then, okay, so that's where you have discussed the example. I hope in the tutorial class also, you have discussed a couple of questions to find the probability values with these sampling distribution. Okay, so I'm not going to go through this one again. Okay, hope it's clear to you. If not, please, you can ask me, or you can ask Ms. Uttara as well. Okay, simply we are finding z values of the given x bar, and then use that one to find the probability. Okay, and this one. Okay, now we are coming to this one. This is the one we couldn't discuss last time. Yeah, so the sampling distribution of the sample proportion. Now here we are considering another statistic called sample population. Okay, sample proportion. Sample proportion. Now let me consider this example. Let's say now, as we are having kind of very hot weather these times, let's say, do you like ice cream? Do you like ice cream? So this is our question. Okay, so let's say we ask this question. Let's say we ask this question from 100 people. Okay, 100 people. So do you like ice cream? So everyone can give yes or no. Okay, so here simply yes, no question. Okay, now let's say we are having a population. This is the population. Let's say the population size is 100. We are using capital N, 100. 100. Let me do, sorry, 100. Okay. Then, now you see, in this population, we have no and yes. Let's say we have, do you like ice cream? Yes, we have, let's say, we have 75 people say yes to this question and 25 no. Okay, say no to this question. Now, similar to the previous example, I'm going to take a sample out of this population. So this is the population. So I'm going to take one sample, sample 1. And here also we have, in the sample also, now we have no years. Let's say in the first sample, we have years. No, we have, let's say, 15. Let me take a sample size of, let me take 30. Okay, sample size of 30. Let's say we have 50 no's and 50 yes. And I'm going to take another sample. Let's say sample 2 with the same sample size 30. And let's say now I have no 25, yes 5. Okay, likewise, we can take sample 3. Sorry. Sample 3, the same sample size, N30. Now let's say we have N5 here, yes, 25. Okay, likewise, now you see here, so this is a yes, no question. Okay, so for this kind of a population where we have two situations, yes, no, okay, so yes, no kind of a situation, we can say yes, 1, no, 0. Okay, we can give a simple number. This is a kind of a binary situation, okay, where we have two classes, yes, no, 1, 0. So for this kind of a population, we can define a sample proportion of success. Okay, sample proportion of success. Sample proportion of success. Now, sample proportion of success here. So let me consider years is the success. Okay, we usually consider the success probability with yes answer. So let me consider yes is P, and we know as we are having. So this is this is the population proportion actually. The population proportion. I'm giving a capital letter P here. The capital letters for the proportion. I mean capital letter for the population proportion of success, P. Okay, simply P will be, capital P will be, we have yes 75 over 100. Okay, and the no will be, we have no, it will be actually 1 minus P. 1 minus P will be 25 over 100. Okay, so this is 1 minus P. Okay, this is a kind of a probability value one, because this is a proportion. Okay, this is a probability value. So similarly, now so we can find, if we consider this sample, for this sample we can calculate. Now for this sample we use this simple P hat. We are using this hat notation for the sample. P simple P hat. මෙතන වෙන්නේ 25 over 30 because the sample size is 30. Out of 30, we have number of yeses, we have 25. And therefore, then 1 minus P hat will be 5 over 30. Okay. So likewise, for each of the sample, we can calculate P hat, 1 minus P hat. So now let's consider P hat will be the sample proportion of success. Sample proportion of success. In a simple random sampling, in a simple random sample here, simple random sample. Simple random sample. Okay. P hat, we call this one as P hat. P hat. Be the sample proportion of success in a simple random sample of size n. For this example, n is 30, drawn from a large population having capital P of success. Capital P of success. Then, now we know, similar to the sample mean example, here also we can take how many samples? We can take infinitely many number of samples. Okay, we can take. Now here we took 3 samples. Likewise, we can take 1,000 samples with again yes, no. Okay. Now if we take, now here, if we take sample 1, sample 2, like like 1,000 samples. And for each of the samples, we can calculate p hat. P hat 1, p hat 2, okay, p hat 100, sorry, 1,000. If we calculate this, the sample proportion of successes, and if we, I mean, similar to the previous example, that sampling distribution of sample mean, now we have 1,000 values. And if we, let's say, if we draw these 1,000 values on a diagram, okay, on a diagram, we can again see, we can again get a shape, or we can define a sampling distribution of p hat. We can, now we say sampling distribution of sample proportion. This is sample proportion. Previously, we discussed sampling distribution of sample mean. Here we consider sampling distribution of sample proportion. Okay, so you should understand in this, I mean, when we consider the sample proportion, we should have simply binary kind of a situation. Yes, no situation. Okay, so sampling distribution of sample proportion, similar to the previous one. Now you should understand, let me write here, sampling distribution, if we consider sampling distribution, sorry, if we consider sampling distribution of x bar, we know sampling distribution of x, I mean, if we consider the sampling distribution of x bar, then the mean of sampling distribution of x bar will be mu. Then the standard deviation of sampling distribution of x bar, we know it's sigma over square root n from the previous topic. Then here we are considering actually sampling distribution. I hope you are taking your own notes. Okay, please take your notes on your own. Okay, so sampling distribution of p hat, sampling distribution of, one moment, sampling distribution of p hat. Then what is the mean of, here the mean of sampling distribution of p hat will be capital P. Capital P. Okay, capital P. Then the standard deviation, similar to the previous distribution, sampling distribution of mean, standard deviation of sampling distribution of p hat will be now, it will be now square root p times 1 minus p over divided by n. Okay, so this is the standard deviation of the sampling distribution of p hat. Okay, similar to the sampling distribution of x bar. මේක තමයි අපේ sampling distribution of x bar වෙන්නේ. Okay, so we gave a special name for this one, standard error of, so this is simply the standard error of x bar. Similarly, we call this part as the standard error of p hat. Standard error of p hat. Okay. Hope it's clear to you. Okay. Okay, I hope you are taking these notes on your notebook. Okay. Okay, next, let's skip to the, I mean, if you want a time, just let me know. Okay, and if you have any question, please stop me and ask. Okay, okay, I hope it's clear to you. Then let me jump into the next slide. Okay, now, similar to the previous one, similar to the sampling distribution of sample mean, again, Here also, we can consider this normal approximation. So let's draw a simple random sample of size n from a large population having a population proportion of success P. Okay. Let me draw that one again. So we are taking a population having a proportion of success P. P. Okay, this is the success probability. Success probability, we can say probability. And let X be the count of success in the sample. So we can take a sample out of this population. This is a sample. And in the sample, we have, again, yes, no kind of a binary situation. So X be the count of success. That means the number of success is X, let's say. So yes, we have yes for X times, yes, X times. So therefore, P hat will be simply X over the sample size. X over the sample size. Okay. So P hat is the sample proportion of success. Then when n is large, that means the sample size. Sample size. Now n is large in statistics. You should understand n should be greater than or equal 30. When n is large, the sampling distribution of sample proportion is approximately normal. We can write, okay, now P hat approximately distributed as normal with population proportion P and the standard deviation, this one. So simply, in the normal population, you should understand, so the normal population or normal distribution, simply we have two parameters, mu and sigma. For a normal distribution, we have two parameters, mu and sigma. Now here, mu will be P, this will be the standard deviation. Standard deviation. Okay, this is the standard deviation value of this population, of this sampling distribution of the sampling distribution of the sample proportion, and this will be the mu. Then there's a rule of thumb for this whole situation. We can use this approximation. Actually, we can use this approximation. Let me erase this part. We can use this approximation. When these two conditions are satisfied. This approximation means this normal approximation. We can use this normal approximation when these two conditions are satisfied. When n times P, n is the sample size, times the population proportion greater than or 10, and n times 1 minus P greater than 10. If these two conditions are satisfied, then we can use this normal approximation. Okay, so now if you want to use this normal approximation, we need to check these two conditions as well. Okay, then so now as we have this normal approximation, we can use again the Z kind of the transformation. How do we use the Z? We subtract, or we take the difference between P hat and the population proportion and divide by the standard deviation. Okay, whole standard deviation. Then we can convert, we can use the Z value and then we can use the Z table. Now let's go to an example. So in this survey, we have female workers ages 20 to 35. 46% say they would rather give up some of their salary for more personal time. Suppose we select, now we have population. Okay. So from this population, 46. So this is population, females, we have females. So this is population. One moment. So this is population. So population contains female, ages from 20 to 35. Okay. And they said they would rather give up some of their salary for more personal time. So 46% is the probability of success. And we have, so this is simply the P. And 1 minus P will be 54%. Okay, this is 1 minus P. And then suppose you select a sample of 400 full-time female workers, 20 to 35 years. So out of this population, we are going to take a sample, let's say sample with sample size 400. Okay, 400. Now here also we have yes, no situation. Okay. Okay, I have a question. Let me check. What's the question, Darua? It is the same Z table. Yes, the same C table. We are going to, yeah. I mean, the C table we are used, I mean, the tables will not, they are not changing the rule. We are using the same C table and whatever the other, I mean, we are going to consider another table, another distribution today. I hope we have time. So we are going to discuss another one also. We are using the same distribution. Okay, we are using the same. Yes. Okay, now here we are again. Okay, so here we are having the situation yes, no. Okay, we don't know the kind of the values. I mean, out of the 400 females, they give up some of their salary for more personal time. That is the yes part, and there are no as well. Okay. Now the question is, what is the probability that in the sample, fewer than 50% would rather give up some of their salary for more personal time? So that means we need to find the probability where X, we need to define X actually. I mean, there's a solution. Let me consider X here. Not X actually, P, sorry, not X, P, proportion P hat. Let me consider proportion P hat as proportion of female workers who would rather give up some of their salary. Okay, you can write that one, some of their salary. So now what we are going to find here, we are going to simply find probability P hat fewer than 50%. Okay, probability that in the sample fewer than 50%. So we are going to find this probability. Okay, now let's go to the solution. Okay, solution, yeah. Solution is given here. So what we need, probability that in the sample of 400 full-time female workers of 20 to 35 years old, fewer than 50% would rather give up some of their salary for more personal time. Okay, so this is the probability that we are interested in. Probability P hat less than 50%, 0.5. Okay, 50% means 0.5. Okay, so simply we are finding probability P hat less than 50%. Now, as in the previous slide, not in this one. Here, to use this approximation, to use this normal approximation, we should check these two conditions. I mean, if these two conditions are satisfied, then we can use this normal approximation, or we can simply convert whatever the p hat values into the z value. Okay, so therefore, let's first check the two conditions. Okay, now here you see, we check the condition NP, N is 400, P is the probability of success in the population. From this example, we have 46% state that they would rather give up some of their salary for more personal time. So this is the probability of success. Okay, 46%. So we know that probability. So in this exam, in this kind of the questions, P should be given. P is from the population data. Okay, so we know the 46%. Okay, 46%. So it's 184. This is definitely greater than 10. Then we can calculate n times 1 minus p. It's 400 times 1 minus p is 54% or 0.54. It's again greater than 10. So therefore, sample size is large enough to assume that the sampling distribution of p hat is approximately normally distributed. Okay. Now, therefore, we can simply find to convert or to use this transformation, we should know P and this square root value. That's what we find here. Simply, the mean of the sampling distribution will be P, that is the 46%. Then the standard deviation of sampling distribution of P hat will be the square root term. We can find that one as well. Okay. Then we are going to find the z value of p hat. So now the p hat is 0.5. P hat is, we are considering simply the p hat value. Okay, p hat, we are finding, we are trying to find fewer than 50%, but here we are, we just ignore this. We just kind of disregard this less than sign, and we take p hat as 0.5. Okay, then p hat 0.5, p we know capital P value, and we know the square root value, and then we find the z value. Now what we do here, now we convert this expression into value with z. Okay, value with z. So p hat less than 0.5 means z less than 1.16. Now we know how to use the Z table. Simply go to the Z table. Let me erase this one. Erase everything. Now go to the Z table. We are going to consider what is the value? 1.61. 1.61 value. So this is the value. This is the value here. Okay, so this is the value. Sorry. This is the value. Okay, this is the value 1.61. 94.63. Okay, 94.63. So therefore, 94.63% of the samples of 400 full-time female workers of 22 to 35 years would be expected to have a sample proportion less than 0.5. So you can write the interpretation of this result. Okay, so 94.63% is the probability. Okay. Yeah, so now as you know how to use the Z table, it's now, you know how to do that, but the new material or new thing here is to kind of how to convert whatever the P hat value to the Z. Okay, using the sampling distribution of sample proportion. Okay, I hope it's clear to you. And Ms. Uttara will also discuss a couple of questions from this sampling proportion part. Okay, and you have two more exercises. So please try these ones as well, and answer is given here. Okay. Okay, now what we are going to discuss, we are going to move to the next topic, confidence interval estimation. So we are going to discuss confidence interval for population mean and the confidence interval for population proportion. So in this class, simply we are considering we are considering simply the mean and the proportions. Those are the only two values that we are considering: population mean, population proportion, or the sample mean or the sample proportion. And we will discuss how to calculate the sample sizes. If you want to calculate the sample mean, if you want to calculate the population mean and the population proportion. Okay, so let's go to the second topic, the confidence interval estimation. So these are the topics that we are going to discuss. Confidence interval, we are going to look at what is the mean of the confidence interval, and confidence interval for population mean, and confidence interval for population proportion, and the sample size determination. So, yeah. So after completing this lesson, you will be able to construct and interpret the confidence interval for the population mean and the population proportion, and determine the sample size that we need to develop a confidence interval for mean and the proportion. Okay, now let's jump into the meaning of confidence interval. So now we discuss how to estimate unknown population parameters. For example, here mu, this is the population mean and this is the population proportion. Okay, so this is the population mean and this is population proportion. Okay, so we estimate unknown population proportion by using either point estimates or interval estimates. Point estimate, I already explained what is point estimate. Point estimate is just a single value. It's just a value of a single sample statistic. For example, sample mean for population mean and the sample proportion for the population proportion. Now let's look at interval estimate. So the confidence interval estimate, or CI, it's a range of numbers, or we call an interval. Okay, interval. So here we have, instead of just one value, let's say we have x bar as 50. Okay, so we can say, okay, so now the mu hat, the estimate of this population mean will also be 50. From this sample mean, we can say, okay, mu hat, this is the estimate value. That's how we use in statistic, estimate of population mean. We use this mu hat notation. Mu hat will be 50. Now, instead of giving just one value, what we do now, we try to find an interval where, let's say now 50, let's say we try to find an interval. Let's say it's from, let's say, 45 to 55. So this means what? Now this means now mu hat, we can take any value in between 45 to 55. Let's use equal sign as well. Any value in between 45 to 55 as the mean value. So simply we are trying to find a range of numbers or an interval. This is actually constructed around a point estimate. Now you see this 50 is also inside this interval. Now here we have 45 and 55. 50 is somewhere here. So we see the sum this point estimate also inside this interval. So this is the point estimate. It's just a single value. And this is our confidence interval. This is our confidence interval. Okay. So confidence interval is constructed such that the probability that the interval includes the population parameter is known. So here we simply find, we are constructing a confidence interval using some kind of a probability. So probability means we can say, you will see how to construct it. We can say, okay, we are 95%. So let's say we use this 95% kind of thing. So we are 95% confident. We are 95% confident that the population mean is in between 45 and 55. So this is the kind of the probability. So we are kind of, we are sure that population mean is in between 45 and 55. So we are sure, 95% we are sure, or we are confident that this is these are the two values that the population mean can take. Okay, so we construct a confidence interval based on some probability. So you will see how to consider, or how we consider this probability to construct the confidence interval in the next few slides. Okay, so yeah, so let's look at the motivating example. So suppose we want to estimate the mean GPA of all students at University of Moratuwa. This is one of the examples that we consider in the previous slides, as in the previous note as well. So we know the mean GPA for all students is, it's an unknown value. It's an unknown population mean. I mean, if we consider the whole population, and if we know the GPA, then if we know the GPA of each of the students, then we can calculate. But it's not possible to consider all these students in University of Moratuwa. Madam, these slides are not in the model. Slides are in the model. Here, you can find that one under this week. This is the current week. Okay, confidence interval estimation. Okay. Hi. Okay. Let me jump into that one. Lecture note. So yeah. So let's say, okay. So the mean GPA of all the students at University of Moratuwa, it's an unknown population mean. Now what we do to calculate or to estimate, the better word is estimate. So to estimate estimate this unknown population mean, what we do, we select a sample of students and compute the sample mean. Let's assume that sample mean is 2.80. Now, as a point estimate for the population mean, we can consider this 2.80. But the question is, how accurate is this 2.80 as an estimate of mu? So therefore, now this is just one single value. We know if we take different samples, we will have different GPA, different mean GPA value. So therefore, so we see some kind of a variability from sample to sample. So this part I forgot to kind of update this one. I will update this one. This is from previous intake. Okay. So now here we don't see any variability. Now, we know if we take different samples, we will have different mean values, different mean GPAs. So therefore, to consider or to take that variability into, to consider that variability from sample to sample, instead of considering the point estimate, now we are going to consider, or now we are going to construct a confidence interval estimate. So we call this one as the confidence interval estimate. So this confidence in the confidence interval estimate, we have a kind of an interval, or we have a range of values for mu, where we consider the variability from sample to sample as well. Okay, so that's why giving a confidence interval is more accurate or more preferable compared to giving a point estimate for a population parameter. So more accurate one is giving a confidence interval estimate compared to the point estimate. Now, if you read, I mean, when you are doing your research, when you are doing your final year research, you will read a lot of kind of the papers related to, related to your project. Then you will see some papers, some authors, in the research section, you will see some authors include the confidence interval for a given parameter, because that is the most preferable one compared to the point estimate. Giving just a single value is not that much accurate. So therefore, we are giving a confidence interval estimate for a population parameter. Okay, so this is the, so yeah, we are still in the example. So when we construct a confidence interval, we indicate confidence of correctly estimating the value of the population parameter. That means, let's say 95% confidence, or you can say 90% confidence, or 99% confidence. So when we are considering a confidence interval, we actually considering some kind of a confidence of correctly estimating the value of the population parameter. So this allows us to say that there is a specified confidence, that means 90%, 95%, or 99%, that the mu is somewhere in the range of the numbers defined by the interval. So after studying today's session, we might find 95% confidence interval. Now for this example, we can say, okay, we are having 95% confidence interval for the mean GPA at University of Moratuwa is in between 2.75 and 2.85. So you see, this is the point estimate, 2.80. That's also inside this interval. This is the confidence interval estimate, and this is the point estimate. Okay. So how do we interpret this interval? We interpret this interval estimate by stating that we are 95% confident that the mean GPA at University of Moratuwa is between 2.75 and 2.85. Okay. Let's see how to consider this 95% confident value to calculate this kind of a confidence interval. Okay, you will see that one when we are calculating the confidence interval. Then a confidence interval uses sample data, of course, as in the previous lecture note or in the previous weeks. We used again sample data to calculate confidence interval. So confidence interval uses sample data to estimate an unknown population parameter with an indication of how accurate the point estimate is and of how confident we are that the result is correct. Okay, so we are using some kind of a confident as well, confident value as well. So the general form of a confidence interval is point estimate. Now you see here, when we are constructing the confidence interval, we are simply try to find the confidence interval around the point estimate. So that's why here we mentioned, yeah, we are constructing the confidence interval around the point estimate. Okay, so that's why always the point estimate is also inside the confidence interval. So here we are having this point estimate 2.80 is inside this confidence interval, confident interval. So the general form of the confident interval is point estimate plus or minus margin of error. So let's see how to calculate the margin error. We will discuss that one later. So the confidence interval is the success rate of the method that produced the interval. Okay, so the confidence interval is the probability that the method will give a correct answer. You will understand once we are discussing whole materials. Okay, now let's see how to calculate confidence interval for the population mean. Now, we are considering two situations here. We are considering two situations. Confidence interval for mu when sigma is known. This is the first case. And the second case when sigma is unknown. We consider two situations. Let's look at the first situation when sigma is known. When sigma is known, 100 times 1 minus alpha. Now this alpha, I forgot whether we consider this alpha before. Let me quickly jump into, I forgot whether I explained that one to you. Yeah, I hope I not, yeah, I hope I haven't explained that one. Anyway, it's okay. It's okay. So I will explain that one again. So here alpha is the kind of, so this part actually this 100 times 1 minus alpha, we call this one as the confidence level. This is the confidence level actually. Let me write it. This part is the confidence level. This is the confidence level. This is actually the 95% or 90% or 99%. Okay. So let's say if this is 95%, if this is 95%, then alpha is simply 5%. 90%, if this confidence level is 90%, then alpha is 10%. If the confidence level is 90%, alpha is 1%. Okay. So in the next topic, we are given a given a special name for this alpha. That's the significance level or error, type 1 error. We will come to this one later. Otherwise, it will be too much for you. So just what you need to understand, we call this 100 times 1 minus alpha is the confidence level. So 95% confidence level means alpha 5% error. Let's consider this one as the error. So 95% confidence means we can make 5% error. 95% confidence level means we can make 10% error. 99% confidence level means we can make 1% error. Okay, so you just think this one as probability of making error. Let me write this one as probability of making an error. Okay, we are given a special name. We'll discuss that one later. So the probability of making an error, 5% if we are under the 95% confidence level, likewise. Okay, I hope it's a bit clear to you. Then, sorry. Now let's see this 100 times 1 minus alpha confidence interval for mu. So you need to kind of remember this one. Right? So here we have x bar plus or minus z. I will explain how to find this z, this part from the z table. We call this one as the critical value of the standard normal distribution for an area alpha over 2 in the upper tail. Here, let me explain that to you. Now we know normal distribution is a symmetric distribution. Okay, this is around 0. Okay, this is the standard normal distribution. We know mu is 0 for a standard normal distribution. Okay, so critical value of the standard normal distribution for an area alpha over 2 in the upper tail. Now, you know, we have two tails. This is the upper tail, this is the lower tail. We call this one as the upper tail. This is the lower tail. Lower tail. So we can have here, let me consider these two areas. Here, let me consider this area and this area. Okay. So now, sorry. So if this is the area alpha over 2. Alpha over 2. Critical value of the standard normal distribution for an area of alpha over 2 in the upper tail. So if this is the alpha over 2, then the value, the C value that we find from the using the Z table, this C value, we call this one as Z alpha over 2. Z alpha over 2. Okay. If we take this one as the alpha over 2, we know this is a symmetric distribution. Therefore, this will be actually negative Z alpha over 2. Negative Z alpha over 2. Now, I'm going to show you how to find that one using the Z table. I will do the class till 3:30 darure. I just want to kind of finish at least this part. So, yeah, let me just show you how to find the Z value. Now, here the alpha, this is the error that we can make, 5% error. If the alpha is 5%, now you know the confidence level is 95%. Okay. Now alpha is 5% now. Alpha over 2 is 5 over 2. It's simply 2.5%. Okay. Now let's see how to, now that means here, this is now, sorry, this is now 2.5% or in proportion wise 0.025, right? Yeah, 0.025. I have a question. Madam, we have math lecture at, oh my goodness, at 3:30. Okay, I will finish maybe 3:25. Come on, nane. Yeah, okay. Okay, I didn't know that Dr. Sulani is taking the class from 3:30. Okay. So I will take maybe, yeah, 5 more minutes. So this is the, okay then, yeah, I will explain this one and then stop. Okay. So alpha over 2 will be 0.025. So let me go to this Z table. Now we are going to find the Z value. Okay. Now let me erase this one here. Now in the previous section, when we use the C table, we know the Z value. We know the Z value and we find the probability. Now here, we know the probability and we are going to find the Z value. That means now we know these values, the values inside or the values in the cells. We know the values in the cell. And now we are going to find the C values, the backward. Okay. Now here, let me draw this one again. So here mu is 0 and we have here 5%. No, 2.5. Okay, that means 0.025. Now we try to find the Z alpha over 2. Okay. Now, again, we are using this what you call the same Z table. Now, if this is 0.025, now we know the area under this region, or area under this part. If this is 0.025, now we know this is 0.975. 0.975. So from this table, we have the area that consider from the left tail. So left tail to this one. So now actually this area is now 0.975. Now we need to find where we can find this 0.975 value inside this table. So 0.975 somewhere here, this one. So we have exactly the 0.975. Then what we do, we read corresponding Z value. So here, this is the 1.96. So corresponding Z value will be, actually this value will be 1.96. So Z alpha over 2 will be 1.96. Okay. Now let's consider another one, another value here. Okay, let me consider alpha as 10%. Okay, then alpha over 2 will be 5%. So therefore, so this is the area now. This is the 5% area. 5% means 0.050. Okay, so this is the Z alpha over 2. Okay, simply this is the alpha over 2. Now, if this is 5%, then we know this is 95%. Area under the other region will be 95%. What is the area actually? 0.950. Now we are going to find where we can find this 950. So 950 somewhere here. Yeah, 950. Now there is no, so we have simply, this is 9495. This is 9505. We can't exactly find 0.950. So you can take either this 1.64 or 1.65. It's okay. So we can take, because we can't, so this 95 is in between these two values. So we can take 1.64 or 1.65. So let me take 1.64. So now the Z alpha over 2 will be 1.64. So likewise, we should know, once you are given the probability, we should know how to find the corresponding C value. Okay? I hope it's clear to you. So, yeah, so that's how we are finding this confidence interval for mu when sigma is known. Once we know the Z value, then we can simply plug in the values here, because we know X bar here, we know X bar, now we know Z alpha over 2, and we are given sigma and the square root 10, then we can find the confidence interval. Okay, then we can find the confidence interval. So, yeah, so the example is given here, how to find the confidence interval. This part, it's just the explanation part. Example, confidence interval for mu when sigma is known. Okay, so then let's stop actually, because you are now going to have a math class as well. So maybe I will meet you, maybe I will take 45 minutes away from the tutorial class to kind of discuss this example. Maybe half an hour විතර I will take to discuss this example, and then Miss Uttara will also discuss more questions. Okay, I will take 30 minutes to kind of from your tutorial class. Right? Or maybe she will also discuss it. But let's see. Okay, then yeah, there's another class. Madam, can you upload? What do you call? Can you upload those two? What do you mean those two? Can you upload those two? Can you? What do you mean by those two? I don't understand what those means. You mean recordings? Not sure. Just type what you need, Tarwa. Okay, so then I will stop here. I will stop here.
Recording stopped.
Yeah, then see you then maybe in your tutorial class, or maybe Miss Tara will also discuss this part. All right. Okay, then have a nice evening. I will upload the recordings. Okay, thank you.